or if I don't get to it in class and we kind of freestyle a little bit, then you at least have all the info. So I'm going to start with chapter 2, fuel for exercise. First chapter, first slide. The fuel for exercise is, I mean, you can't just do activity. A car can't just move forward. There are things that make a car move forward. And the things that make a car move forward are the wheels and the steering wheel and even the seats. I mean, you can't sit on the floor, but you also have to have some fuel. And the fuel is gasoline. And gasoline has, a different, it has a chemical structure to it, and the chemical structure breaks apart. And when the chemical structure breaks apart, energy is released. All right, and that energy goes to making an explosion inside the engine, so that a piston fires up, and then that like moves gears, and when the gears move, the car moves. So it's the explosion of the gasoline that creates the energy for the car to move. So I mean, we don't guzzle gasoline, so we eat food, and the food that we eat breaks down in chemical reactions, and eventually it all breaks down to ATP, and ATP is pretty much the gasoline. And when the ATP breaks apart, it causes things to move, like an explosion would cause the trees around it to fold out. Like energy release creates movement. So we're just going to talk about how you get ATP pretty much in chapter 2. Next slide in chapter 2. That's really pretty much the first slide. There are substrates. Substrates are fuels for exercise. It's pretty much your micro and your macronutrients. You have to eat most of the substrates in massive quantities, because, like, particularly fat, protein, and carbohydrate in massive quantities, because you need a lot of energy. I mean, a typical adult has 2,000 calories a day. And for the most part, the gymnasts that I have, even though they're 10 to 18, they're probably at 4,000 calories a day. So what you have to do is be able to store that energy. You have to be able to break that energy down. And the energy breakdown in a biological system is called bioenergetics. Next slide is talks about substrates and goes into some definitions. So substrates are fuel sources that eventually we need to break down to carbohydrate, to ATP. Now, the fuel sources are going to be carbohydrate, protein, and fat. Carbohydrate is made of carbon, hydrogen, and oxygen. So is fat, but it just has a bunch of different bondings and this and that. And for the most part, so is protein. Protein has carbon, hydrogen, oxygen, but it also has an amine group. So the amine group has to get ripped off of the protein before the protein can get used for energy. That actually costs the body a little bit of, like, actually, it's an exogenic action. It actually endogenic. I don't know. We'll get into that later. Endogenic reaction. It's a reaction that costs the body energy. So the body doesn't want to spend energy to break protein down for energy. It's like a negative in the negative in the energy field pool twice as much. So the body doesn't want to do that. So the body would prefer to break down carbohydrate and fat, and carbohydrate is such a good fuel that as your body becomes a better and better athlete, it's going to want to save carbohydrate for more intense activities, and it'll just use like whatever carbohydrate it needs, and some of the fat stores actually at moderate to low activities. So carbohydrate is like a high octane fuel that the body wants to use, but it wants to store because it's such a good fuel. Bioenergetics is the process of using all of this fuel, breaking it down, digesting it, absorbing it into the bloodstream, so eventually all that fuel can be used for energy. It's all the processes using energy in the entire body, the breakdown of carbohydrate, protein, and fat, and the build up of ATP. That's all called metabolism. There are catabolic processes and there are anabolic processes. The catabolic processes are going to take a big molecule and break it down into a small molecule. And the anabolic processes are going to make something small and build it up, like an anabolic steroid. Makes tissue small and builds it up. A catabolic process is the breakdown of ATP. When ATP starts with adenosine triphosphate and one of the phosphates is ripped off, that's a catabolic process because a molecule goes from a particular size and gets smaller. But for instance, another anabolic process would be the formation of ATP from adenosine diphosphate, where there's an extra phosphate group and it attaches to the adenosine diphosphate group to become ATP. So metabolism is the total sum of all of the catabolic and anabolic processes that are occurring through the body. Now I'm on chapter 4. You can calculate energy. All right, energy is like if I take a piece of material and I burn it, there's going to be like a fire and smoke, and that fire and smoke is energy. And if I can capture how much energy is in that fire, then I can have an estimate of how much energy is in that particular material. And the way to do that is, indeed, what you do is you put a piece of material in what's called a direct calorimeter, and you burn it. And the calorimeter is going to be like a chamber surrounded by water. And when you burn it, the water is going to increase in temperature. 1 calorie is the heat required to increase the temperature of the water surrounding that particular pan or whatever, that particular, the calorimeter by it's to raise 1 gram of water from 14.5 centigrade to 15.5 centigrade. 1 calorie is equal to 1 kilocalorie, but pretty much we call kilocalories, and this is a little bit confusing, calories. So if somebody's talking about 500 kilocalories, they're actually talking about 1 dietary calorie. So 1,000 cal equals 1 kilocal, and 1 kilocal is equal to 1 calorie, which is silly. But anyway. Now I'm on slide 5. You're going to have pretty much 3 main substrates for energy. You can get carbohydrate, fat, and protein. They're all pretty much made of carbon, hydrogen, oxygen, and like I said before, protein has this nitrogen group. The nitrogen group is ripped off, it costs energy, and then that nitrogen group combines with ammonia to become uric acid, and then you just urinate it out. So even if you eat excess protein, you don't really necessarily store it. You just kind of use whatever you need for energy, and the rest of the excess protein you pretty much get rid of. There are chemical bonds that are between each of the carbon, hydrogen, and oxygen molecules, and when the chemical bonds are ripped apart, there's energy released, and that energy is used to reform ATP from ADP, and then the ATP is ripped off, and the phosphate groups are ripped off, and that energy released from those bonds is where the myosin cross bridges is what the myosin cross bridges use to change their angle of orientation. At rest, usually people want to have about 50% carbohydrate and 50% fat, but at rest you're using about 50% carbohydrate and 50% fat, but those percentages change. In fact, when you're eating, you should, like a regular diet, you should have about 50% carbohydrate, 30% fat, and 20% protein, because we're not really resting all of the time. So rather than burning 50% carbohydrate, 50% fat, when you're moving around, you're actually spending a little bit more carbohydrate. Exercise that lasts short term, you're going to use a little bit more carbohydrate stores, but exercise that lasts for a long time, you're going to have to use a little bit of your fat stores because your carbohydrate stores are going to dwindle over time. So another fuel source is going to have to be used. All right, now I'm on the 6th slide. Carbohydrate is all broken down into glucose. Glucose is the most simple carbohydrate, C6H12O6, and that's a 6-carbon molecule. That 6-carbon molecule is going to be broken in half into what's called a pyruvate. There are 4 kilocalories for every gram of carbohydrate. So there's actually more energy stored in fat than there is, I meant, so the next thing that's important is that the glucose is the only carbohydrate that's used directly for energy by the central nervous system. So central nervous system will not use protein and fat as a fuel source. So sometimes when you hear about like low carbohydrate diets and things like that, I'm a little bit weary of that because just because of this slide right over here, it says it's a primary ATP source for the muscles and the brain. If the brain only uses this for ATP, then I want to nourish my brain. I don't want to have a low carb diet because I'm going to tend to fall asleep in class. I'm going to tend to not be able to concentrate and things like that. So I want to fuel my brain. So I want to make sure that I have carbohydrate. Eventually, extra glucose that's stored in your body, it's like a cache of energy. So your body doesn't want to get rid of it. So your body is going to store excess sugar. Takes the excess sugar, brings it to your liver, and the liver breaks it down into adipose fat. So if you eat more sugar and you do less exercise, then your body's going to obviously store more and more and more of that sugar, and it's potentially, actually, the sugar in our diet that's making people fat as opposed to the fats in our diet. The fats in our diet are leading to cardiovascular disease, but that's a different story. Okay, so now I'm on to slide 7. Fat. It's a very, very efficient store of energy. You can store more than twice as much energy in 1 gram of fat than you can in 1 gram of carbohydrate. So your body doesn't try to stockpile carbohydrate. It tries to take carbohydrate and make it into fat. Diabetes is when you can't really do that anymore. I mean, I don't want to say that. It's like there's so much more to diabetes. It's when your pancreas can't, you have insulin insensitivity, all sorts of stuff. But when your body, the amount of glucose in your bloodstream just keeps stockpiling and stockpiling and stockpiling, and it's not turned to fat because either you can't make enough like adipose fat, or because insulin sensitivity is way off. I mean, that's going to start to stockpile sugar in your bloodstream, make your blood glucose levels rise and rise and rise, and when they get past a particular level, that's pretty much what the symptoms of type 2 diabetes. So your body stores much more energy as fat in the body as it does in terms of carbohydrate. In fact, you have about 70,000 kilocalories stored as fat versus about 2,500 kilocalories stored as carbohydrate. Your body, like I said, your body wants to save carbohydrate so that it can use it when it really needs. It's like the high octane fuel, so you want to use carbohydrate when you're really running for a long period of time at a pretty high intensity. But fat is kind of such a good energy store and a good source of energy that your body is just going to use that predominantly at lower long-term kind of exercises. So what I would have people do if they wanted to lose a little bit of weight or manage their weight is they don't have to run on a treadmill. What they could do is they could, walk 4 or 5 times a day, 4 or 5 times a week at like a low 3.5 miles per hour, maybe even 3 miles per hour on a treadmill, and make sure that they limit the amount of sugar intake and that they do exercise so that the sugar has an opportunity to get broken down for energy and stored as adipose fat at a less potential. All right, so fats are called triglycerols too, triacylglycerols, and that means that there's a 3-acyl group, a 3 fatty acid group, and they're all attached to this like glycerol backbone. So in order for the fat to be used, those 3 fatty acids have to be ripped off of the glycerol backbone, and then the fatty acids are going to go through a process called beta oxidation, and that is where the fat is goes through processes so that the fat can go into the mitochondria and be broken down for ATP. So the free fatty acids are the things that are broken down to ATP, and the glycerol is going to be it's going to end up combining with other protein resources, and eventually it's going to probably be used to make some more sugars if the sugar stores in your body get low. So that's probably the extra glycerol is going to go into gluconeogenesis. That's what that process is called. All right, now I'm on table 2.1. It shows you how much energy is stored in your liver, muscle, and glucose in terms of carbohydrate. You can see the total number of calories there in terms of carbohydrate stores is, about 3,000 calories. But if you compare that to the amount of fat under your skin, which is visceral fat, and the fat that's in your muscle, then you can see that's about, visceral fat is fat that's around your abdomen, sorry. Subcutaneous fat is fat that's under your skin. Visceral fat is different because it has a direct connection to, is very, very close to where your liver is and your portal vein. So there's, the visceral fat breaks down at a different rate than your subcutaneous fat. So that's the distinction there. You can see that you can store much more energy, and your body does store much more energy as fat than it does carbohydrate. It's a much better energy store. All right, now we're on slide 9. Talks about protein. Protein has very similar energy storage characteristics as carbohydrate. You store about 4 calories per gram. So your body doesn't stockpile protein necessarily either, unless you're doing things like hypertrophy training and such that we'll get into later on in the semester. But before the protein can be used, it needs to be broken down into, again, glucose. They're all broken down into glucose: carbohydrate, protein, and fat. A protein has amino acids, and those amino acids have amine groups. And those amine groups need to be pulled off of the amino acid before the amino acid can be put into the Krebs cycle and used for energy. So through lipogenesis, some of the protein can also be converted to free fatty acids and stored as energy or used for energy. The 10th slide shows you that pretty much food intake, fats, carbohydrates, and proteins. Proteins are broken down into amino acids. Glucose is broken down into eventually pyruvate, which is brought into the mitochondria and broken down into acetyl-CoA. And fatty acids they go through this process called lipolysis, which breaks lipolysis, which is the breakdown of fats into the free fatty acids, and then those free fatty acids can go through lipogenesis, which is the making of fats from like bits and pieces and resources of fats that are kind of floating around the bloodstream. Same thing with glycogenesis and gluconeogenesis. Glycogenesis is once you've stored fat as adipose fat, you can take that fat and make it back into glucose. And gluconeogenesis is after the breakdown of fatty acids and proteins and carbohydrate. There's going to be like remnants of all of those things floating through the bloodstream, and those things will combine eventually through chemical processes to make new glucose, and that's called gluconeogenesis. Gluco is sugar, and neo is like all sorts of new stuff, new, and genesis, the new creation of glucose from stuff that's everywhere else. So, all right, next slide, chapter 11, energy related mass action effect. More of those. If there's more energy available, there's more activity. I don't know. I have to take a look at this slide, honestly.